This is AP Calculus. We're doing section 1.4. So as often happens in my class, I will cover things when they sort of naturally come up, and what that does in terms of our pacing is that sometimes it means we get to a section where we've inadvertently covered a lot of the material in the section, even though we just started the section. Ignore the huffing and puffing of my very old dog on this very hot day because he is sitting on a couch a couple feet from the computer. So I apologize in advance if you hear what sounds like an asthmatic dog. It is my very old lab mix. So anyway, say hi to Bailey. He's tired and huffing and puffing. So anyway, so we have two basic topics that we're going to cover in 1.4. One of them is continuity and one-sided limits, and the reason I mentioned that we have covered part of this before is because in 1.2 you're going to find that we did a good amount of this stuff, but not all of it. So we kind of skimmed the surface, maybe did about half of the material included in 1.2 when we talked about limits the first time. And then the second thing we're going to talk about is the intermediate value theorem, often abbreviated the IVT, and that's going to be on your AP. So I'm just going to throw that out there now. It's very likely that you're going to see either the IVT or some other theorem on your AP. I would say you've probably got a better than 60% chance that it's the IVT, maybe even higher than that, to be honest. Okay, so let's start with talking about this continuity stuff. So in the 1.2 videos, we learned about the actual definition of continuity, which is that the left-sided limit of a function and the right-sided limit of the function and the double-sided limit of the function and the actual value of the function, all of those things are the same at some point A. That means that this function, f of x, is continuous at x equals a. So the honest answer is that the vast majority of functions that we're going to use in calculus and in most of what we're dealing with are going to be continuous functions. Occasionally they'll have vertical asymptotes, which we'll talk about in a sec. But most of our functions don't have jumps naturally and don't have holes, or holes with lids or any stuff like that. Now, it does turn out that sometimes they do, but most of the time we're dealing with a lot of continuous functions. And even when we're dealing with ones that do have these discontinuities, what's going to happen is you're going to have a function that is happy and continuous everywhere else except for one weird spot where it's got a vertical asymptote or where it's got a jump or where it's got a hole or it's got this hole with a lid. So when we discuss the discontinuities, or we rather discuss the continuity of a function, sometimes you'll hear discuss or describe the continuity of a function. What we usually do is we don't list all the places that it's continuous. Rather, we say, hey, this function is happy and continuous everywhere, except, and then we list the spots where there's a problem. It's sort of like if you're listing your food allergies, right? If you're allergic to like shellfish and, I don't know, peanuts, you don't list all of the foods that you can eat. You just say, oh, I can't eat these two things, right? I can't eat shellfish and I can't eat peanuts. You don't spend like the rest of your life listing infinite things you can eat. You list the few things you can't. So we're going to walk through this, but let's talk about the two big types of discontinuities. So discontinuities can be categorized into what we call non-removable or removable. Now, those two words can also be interchanged with essential, so non-removable being essential and removable being non-essential. So in the non-removable discontinuity category, we have vertical asymptotes, right? So for example, if I gave you the graph y equals 1 over x, right? There would be a vertical asymptote at 0. And this graph would have a non-removable discontinuity right here at x equals 0, right? And then we have jumps, right? We've seen some jumps. Most of the time when you have a jump, they're fairly contrived. Like I give you some function that's piecewise, and I tell you that this function is like negative x for x values that are less than 0, and then x plus 5 for x values greater than or equal to 0, and that's going to create a jump because it's going to look like this. Something like that, right? Which will have a jump at x equals 0. Okay, and I'll show you other ways that we can see jumps naturally using what we call the greatest integer less than function and some other things like that. We also saw in a previous video, probably 1.3, I think, we saw that we have a jump discontinuity if we graph this, right? That this thing graphs, oh my goodness, my dog is having like an asthma attack. Okay, that it graphs like this, and you'll see there's a jump discontinuity at 0. The other category of discontinuities is called removable. Again, some books will call that non-essential. So what you're going to find is that a book either uses these two terms, right, non-removable and removable, or these two terms, essential and non-essential. Same thing with an exam. Typically, we use the same language consistently. But I wanted you to see both just in case. So holes are an example of sort of like they're like a pothole in the middle of a graph, right? So it's just a little teeny piece of the graph that's missing. In fact, it's such an infinitesimally small piece that in reality you couldn't see this with the naked eye. Like we draw this big obnoxious circle, but really it's a little infinitesimally small prick of the graph that's missing, like a pinprick in the graph that's missing, okay? So those are holes. One way to think about this logically, if you're trying to think about like which one sounds like it's more serious, removable discontinuities don't create very big problems for us. They're actually really easy to deal with. And one way to think about that is if you're driving down a road and you see a pothole, I mean, if you live in Philly, you definitely know what a pothole looks like. It's not a big deal. You can probably keep driving on the road, right? Nothing tragic's gonna happen. But if you're driving down the road and you see a massive cliff that if you drive off it, you're gonna it's not gonna go well, right? If you're like, hey, this is me driving off the road and here's the road down here and you're just driving along, unless you're in like a 90s action movie, that's not gonna end well, right? And the same thing with vertical asymptotes, right? Like this goes up forever and then would drop off precipitously down to the bottom. So one way to think about the severity of these discontinuities is like, hey, if I were a car driving on the graph, what would happen? And removable discontinuities are much easier to deal with than non-removable discontinuities. Cool. So we did also talk about one-sided limits a little bit, but we can revisit that just in case to make sure we're comfortable with it if we need to. So before we do that, let's describe the continuity of some things. So when we hear the phrase describe, this is just scribble, guys. My brain's done. Describe. Sometimes you'll hear describe, sometimes you'll hear discuss, right? Or like some other version of this word, right? So describe, discuss the continuity. When you hear this, what it basically means is you want to determine the locations of the discontinuities. I'm just going to say disc because I'm lazy. And say that everything's fine elsewhere. Something akin to continuous for all of other x, okay? So for example, let's go ahead and call this an example 1. So we're going to describe/discuss the continuity. So the function I'm going to give you is f of x equals a 5 on top of an x minus 3. So fundamentally, almost all of our discontinuities happen when we try to divide by 0, right? So the short answer is that discontinuities that are vertical asymptotes or holes are pretty much just, hey, the denominator is equal to 0. Like, that's the problem. When the denominator is equal to 0, we might have a vertical asymptote or a hole, and we're going to revisit a couple options like that. The other option is if you have some kind of a piecewise function, you have to check for jumps. All right, and those are the only real places that you're going to see that there could be discontinuities. So in example 1, if we look at example 1, the only real issue I could possibly have is that this denominator could be 0, and there's going to be a vertical asymptote when x minus 3 is a 0, right? What makes it a vertical asymptote is essentially a factor in the denominator that does not cancel from the numerator. So there's a vertical asymptote at x equals 3. So f of x is continuous for all x except there is a non-removable discontinuity at x equals 3. Okay, non-removable discontinuity at x equals 3. And specifically, if you wanted to write what it is, it's a vertical asymptote. Right? So I'm going to give you a P1 that's similar, and if you want to pause me, you can. So let's call this one g of x, and let's do 5. Oh, I just did a 5. That's cool. We'll do it anyway. 5x over 2x plus 8. Great. Okay, so discuss the continuity of this function. Again, remember that disproportionately discontinuities are just when the denominator of a function equals 0. So pause me if you want. I'm going to go ahead and do this problem. So in this situation, this factor on the bottom, this 2x plus 8 equals 0 would give me a vertical asymptote at x equals negative 4. So g of x is continuous for all x except not how you spell any of those words, except there is a non-removable discontinuity at x equals -4. And I was kind of lazy with my notation, but we'll survive. All right. So most of the time, you're not going to be asked to discuss the continuity of these functions once you get past the very basic problems that you're doing in like practice problems. You're not going to see them on an actual AP, but it's a good idea to understand where discontinuities happen. So just to show you another option, if this is a calculator section, or I guess you could graph it by hand, but it would be kind of miserable. If I were to look at E1 as a graph on my calculator, I would type in 5 divided by, and then in parentheses, the x minus 3, right, because that whole thing's in the denominator, and I'd probably zoom 6. And sure enough, what you'll see is a graph that has a vertical asymptote, and you can see that line right there at x equals 3, and everywhere else it seems to be a nice happy function where I wouldn't have to lift up my pen. So again, if it helps you, you can see that what this graph looks like is this vertical asymptote at 3, and then it kind of looks like this. Okay, so everywhere else, nice happy function, but at 3 there's a vertical asymptote. And you can see the same thing would be true if I type in what I had for P1, 2x plus 8, right? So that's what I've got for my P1, and I go ahead and hit graph. And sure enough, you'll see that at x equals -4, there is a vertical asymptote. And so same idea, right? So somewhere around here, -4, my graph looks like this, right? I did a bad job, but you get the gist of it. So anyway, vertical asymptote at x equals -4. So if you're asked to discuss the continuity, you're mostly just listing where functions have problems, right? Now let's do an example where we talk about having some holes, because that's the next kind of discontinuity I want to mention. Okay, so if you think back to Algebra 2, specifically if you had me, it's our section 8.2 in Algebra 2. We're still going to be discussing the discontinuity, but let's do an h of x equals x plus 1 over x squared plus 3x plus 2. Cool. All right. So the trick with this graph, right? This graph's actually going to have both a hole and a vertical asymptote, right? So if you were to factor this denominator, it's going to factor into an x plus 1 and an x plus 2. This factor that cancels is going to give me a hole in the graph. So there's a hole when x plus 1 equals 0, which is at x equals -1. And the factor in the denominator that doesn't cancel is going to give me a vertical asymptote. And again, this is something that you cover in Algebra 2, but I get that it might be a little bit rusty. If you were to graph what this function looks like, it's going to look something like this. And again, I've been doing a lot of math for a lot of years, so that's the reason I can graph something like this pretty much from my head, right? But if you were to put it in your calculator and graph it, you'd put the x plus 1 in the numerator in parentheses, and then on the bottom you'd have an x squared plus 3x plus 2, right? And if I graph, you're going to see that this graph looks an awful lot like the graph that I just drew. Now what you will find is that you can't actually see this hole. The only way to confirm that that hole is there is to actually hit the trace button and then know that the hole's at -1 and check and see, and you'll see that when I do that, there's no y value, right? Because there is no y value at all. If I were describing this continuity, I would say something like continuous for all x except, that's not how you spell that word, there is a non-removable discontinuity. I'm just going to be lazy and write non-removable discontinuity at x equals -2, and there is a removable discontinuity at x equals -1. Now, if I were doing this on an exam, I would write the words out. I'm just being a little bit lazy here because I have a short amount of space. So if I'm describing the continuity, this is my continuity, right? I list the places I have problems. I say whether they are removable or non-removable. I'm going to give you a P2 to try that's similar. So let's see, we'll do j of x equals x minus 2 over x squared minus 4, okay? So there you go. Give this a try on your own. Pause me if you want, and I'm going to go ahead and do the problem. So this is another problem where I'm going to have a factor factor on the bottom that cancels from the top, because this is an x plus 2, x minus 2. This is a difference of squares. So this factor is going to cancel, meaning that when x minus 2 is 0, I have a hole. So there's going to be a hole at x equals 2. And when x plus 2 is 0, I'm going to have a vertical asymptote, so x equals negative 2 is a vertical asymptote. If you were to look at this graph, it's going to have the vertical asymptote at negative 2. It's going to look very similar to the one I just drew, except the hole is going to be at 2. So it's going to look something like this. So again, if I were going to describe it, I would essentially do the exact same description that I just did, right? Except, so I would say continuous for all x, except there is a non-removable discontinuity at x equals negative 2, and there's a removable discontinuity at x equals 2, right? So that would be how I would describe the continuity, okay? Again, you're not really going to be asked to do this once you get through probably this section in all likelihood. I don't expect you to see an AP that asks you to describe the continuity specifically. What is important to us on AP exams and also later moving forward is that almost every theorem you're going to use in calculus, including this intermediate value theorem, relies on the function being continuous in the window you're looking at. So if you're looking at a window from x equals a to x equals b, your function has to be continuous on that window for the theorem to apply. So while I'm not generally going to make you describe the continuity of a function, and the AP won't either, if you're asked whether a theorem applies, and that's a very realistic AP question, and the answer is no because of a discontinuity, you need to be able to explain that, right? So you need to be able to understand what the continuity of a function is. You're not probably going to be asked this exact question where you're asked to explain it. You will be asked to check and see if a function is continuous to apply a theorem. They're not specifically asking you to check continuity, but if the continuity is an issue, then you're going to have to point that out, if that makes any sense. Okay, so let's talk about one other kind of discontinuity, and then we'll probably stop this video and go ahead and make another one. All right, so let's talk about some jump discontinuities. So jump discontinuities are the only ones we haven't talked about. Now, they occur in two big kinds of ways. Jump discontinuities, so when we talk about jumps, okay, they basically happen in two big ways. Number one, piecewise functions, and that does include absolute values as we've seen, right? So piecewise function, which for the record includes absolute values, right? They're piecewise by nature. And the second big way you're going to see it is what I'm going to call the round down. So we're going to say rounding functions. So you've seen this also in Algebra 2 in all likelihood. So these brackets, right, or in your calculator, it's called int, okay? What this means is round x down to the closest integer. So it's actually called the greatest integer less than function. So greatest integer less than function, which is a ridiculous mouthful, which is why we don't feel like saying that, okay? So rounding functions, what you're going to find is that they also give you these weird jumps. So let me just show you what this thing would look like if I gave you this round down function. Again, you're not actually going to see the round down function in a calculus class most of the time. And the reason for that is because in calc, we are disproportionately working with functions that are either continuous all the time or are continuous most of the time. And this thing is not continuous for very large chunks of its domain, right? So basically what happens is, if you look at this, and I'm going to give you some x values to plug in just to show you how this works. So let's pick negative 1, negative 0.8, negative 0.5, negative 0.2, 0, 0.2, 0.5, 0.8. And again, this seems kind of tedious, but in case you've forgotten how this function works, I just want to show you how it works. So 1, 1.2, 1.5, 1.8. And I am intentionally picking some values, 2.2, 2.5, 2.8. Okay, I'm intentionally picking some values that would round in the other direction from what you're seeing to make my point. Okay, so if I were going to round negative 1 down to the nearest integer, it would still be negative 1, right? Because negative 1 is an integer, so it stays there. But if I asked you to round down negative 0.8, so here's negative 1 and here's 0. Here's where negative 0.8 lives, right? If I'm rounding that down to the nearest integer, it's going to be a negative 1. In fact, so will negative 0.5 and so will negative 0.2. They're all going to round down to a negative 1. Once I get to 0, though, 0 is an integer, so 0 will round down to itself, like it is the nearest integer. But then if you look at the numbers 0.2, 0.5, and 0.8, these guys are all going to round down to 0, right? If you then look at the numbers from 1 to 2, here's 1.2, 1.5, 1.8, all of them are going to round down to 1. So all of these numbers are a 1. And all of these numbers are going to be a 2, and then the second we get to 3, we're going to jump to 3. So what this makes is a graph, just to show you. Again, you're not going to see this very often, but it does come up occasionally, and I want to make sure that you're familiar with it because that's part of my job. If you were to graph this, what you're going to find is that starting at -1, -1, you have a point. It's going to go over at -1 until it gets to 0, but then at 0, it's going to jump up to 0 and then go over till it hits 1. When it will jump up at 1. And so what you have is what we often call a step function. So the other name for this is one of many examples of what we call a step function because it looks like actual stairs, okay? So if you have a step function, I want you to notice that this doesn't just have one jump discontinuity. If I were describing the continuity of this function, I would have to say that this thing is discontinuous at every single integer, right? This thing has a jump forever and always at every integer. So if I were asked to describe the continuity of this function, right, so again, we're talking about this rounding function right here. If I were asked to describe the continuity, I would say that this is continuous for all x except, and then you can actually write this in sort of a clever way. I could write it as x is an element of z. Okay, so z is the mathematical abbreviation for the set of numbers that are integers. The other way to write that, if you're like, hey, Hogan, I don't like this, that's too mathy, is except for integer values of x, right? Integer values of x, which are non-removable discontinuities, right? Because there's a jump at every single integer value of x. Again, I'm not going to make you describe this very much, and I don't think you're likely to see a rounding function, one of these greatest integer less than or least integer greater than, whatever. Rounding functions do actually have a function in the business world. If you think about making like a call that's charged, you're usually charged as soon as you go over a full minute, right? Like if you're on a call and it costs so much per minute, the second you hit a minute and a second, you're charged for the full second minute, right? And then the second that you go past that second minute, you're now charged for the whole third minute. That's a round up function, right? It's actually rounding values up. So you will see rounding functions often in a business world, but really, realistically for us in calc, it's not a big deal. Last thing, before we go ahead and do the second video in this section, which will be the IVT, let's do a piecewise function and see how we can see that it has a jump. And so then after this, we'll talk a little bit more about continuity in the second video, and we'll talk about the intermediate value theorem. So an example of piecewise functions, right? So just an example of a step function. So the trick with a piecewise function is if the individual pieces are continuous, you really only have to check where the function has what we would call a breakpoint. You know what? Actually, I'm going to save discussing piecewise functions for our second video. Sorry, guys, I changed my mind. I want to talk about something else before I talk about them. So I'm going to save that for our next video, and bye.